Hello friends, welcome to this new video lecture on advanced algorithm. In this video lecture, we are going to cover the topic red-black tree insertion. So to understand red-black tree, we are going to understand the trees from binary search tree to AVL tree and then to red-black tree. So why are we doing so? To understand that why red-black trees are better than both binary search tree and AVL tree. So let's get started by understanding the differences between the basic trees, that is the binary search tree and AVL tree. So in this particular table, you could see there is a difference between binary search tree and AVL tree. Now, so is binary search tree a binary tree? So now what is a binary tree? In a binary tree, you have the parent, you have the left node, you have the right node. Now, the parent is having a certain value. So the left child of the parent has to have a value lesser than that of the parent. The right node should have a value which is greater than that of the parent. So this is how the binary tree is constructed. So does binary search tree follow the rules of binary tree? Yes, it does. Does AVL tree follows the rule of binary tree? Yes, it does. It has the left node which is having a lesser value than the parent and the right node having a value greater than that of the parent. Now, is there any concept of balancing factor in binary search tree? No, there is not. Is there in AVL tree? Yes, it is. It is strictly balanced binary tree. So what is a balancing factor? It just means that a parent has a left subtree and a right subtree. So the concept is that the difference of the height of the left subtree and the right subtree should not exceed by more than 1. If that is the case, that means that the particular tree is balanced. If it is more than 1, it means it is not balanced. So let's understand. Now, can they be interchangeable? That means, can binary search tree be converted into AVL tree? Now, the AVL tree is a strictly balanced tree and binary search tree is not. So, for BST is not a balanced tree, it can never be interchanged into an AVL tree, wherein AVL tree is always balanced. So, yes, it can be interchanged into a binary search tree, right? Now, the structure of a node in binary search tree has to have only three fields. That is the data field, right? Then a pointer to the left child and a pointer to the right child. But wherein in AVL trees, we have four fields. The left pointer to the left child, the data, the pointer to the right child, and then the balancing factor. I'll repeat again what is balancing factor. It is the difference between the height of the left subtree and of the right subtree. So parent will check for the left subtree, the height of it, and the height of the right subtree, and finally the difference between the height of it will be stored as the balancing factor, and it will ensure that the difference doesn't exceed 1. Now, is binary search tree a balanced tree? Obviously not. And is AVL tree a balanced tree? Yes, it is. Now, the implementation of binary search tree is simple because it need not ensure that the tree is balanced. But in case of AVL tree, it has to ensure. So it is complex. Now, the height of the binary search tree, you'll see that in the worst case, it can go up to big O of n. We'll understand this with the help of an example. But in an AVL tree, as it is a surely balanced, strictly balanced tree, it will never go above big O of log n. Now, does insertion requires balancing in binary search tree? No, it does not. In AVL tree, yes, it does. So there's a concept of rotation that we'll be continuously doing in AVL trees. So there are four types of rotation basically: the left-left rotation, the left-right rotation, the right-right rotation, and then the right-left rotation. So we call it the LL, the LR, the RL, and the RR. Right? Now, is searching efficient? Okay, if you have large number nodes in binary search tree, it is not, because obviously the height of the tree could go till n, so the searching might get affected. But in the case of AVL tree, the height is never going to be more than big of log n, so obviously the searching will be way faster as compared to binary search tree. Now, in the worst case scenario, the insertion, deletion, and searching, all three for binary search tree can go up to big of n, but wherein for AVL trees, it is not going to exceed big O of log n. Now, so let's understand this with the help of an example. So you can see this question wherein I've asked, like, does the order of insertion matters in binary search tree? So you can see it does matter, because now when the inputs are D, B, F, A, C, E, G, so the D becomes the root node, B, which is less than D, comes to the left, You can see F, which is obviously greater than D, so it goes to the right of it. Then we have A. When A comes, it is compared with D. A is less than D. A is again less than B, so it goes to the left. Then you have C, which is less than D, so it comes to B, but it is greater than B, so it goes to the right of B. Similarly, E and G are located, right? Inserted. So yes, this is the case of balanced tree when the inputs are in this sequence. But what if the input are in this sequence? So you can clearly see you have B, then you have A to the left of B, then the D comes, which goes to the right, then you have C, which goes to the right of B because it is greater than B but less than D, so it goes to the left. Then you have G, which is greater than B and D, so it goes to the right. Then you have F, which is greater than D, so it goes to G, but it's less than G, so it comes to the left of G. Similarly, E, which is greater than B, greater than D, less than G, less than F, so it comes over here. So you can see this is not a balanced tree. Similarly, in the case when the inputs are in this form, you can see A comes, then when B comes, it goes to the right of A. When C comes, it goes to the right of A and to the right of B. Then when D comes, it goes to the right of A, B, C, and such is the tree created. Now you can clearly see the height of the tree is equivalent to the number of elements inserted. So obviously the order of the input matters a lot. So you need to clearly understand that the worst case scenario can lead up to big of n in binary search tree, which is not the case in avial tree because it is a balanced tree. Now, so what is the difference between avial tree and balanced red black tree? So you need to understand that we move from binary search tree to avial trees because avial trees are better. They are balanced. The complexity is less. The only thing is the insertion is a bit complex process. But now we see that in avial trees, the complexity is still higher because there is a lot of rotations happening at the time of insertions. So can we reduce them? Okay, so let's understand this. Avial trees are more rigidly balanced and hence provides faster lookups. That means that if you want to search anything in avial tree, it will be very fast because the height is surely not going to be more than log of n. So it is a lookup intensive tree, wherein if you have any lookup intensive task, you should be having avial trees. But obviously insertion is going to be very hectic, a lot of rotations. To reduce this rotations, we have a concept of coloring, which is used in red black trees. So red black trees has both coloring as well as rotations. But yes, the number of rotations reduces a lot. Because of that, we can say that if you have an insert intensive task, you should go for red black tree. And let me tell you, the complexity of red black tree or the height of red black tree is almost approximately equal to log of n. So it is not something which is going to go till n. It is just going to be more than log n or equal to log n, but not too much than log n. It's going to be very near to log of n, even if it is greater. So let's understand what is red black tree. So these are the properties that every single node in the red black tree has to either have a red color or a black color. So there are two colors, the red color and then the black color. Now the root of the tree has to be of the black color. Now the third point is very important, that there should be no red parent-child relationship. Then that means there shouldn't be any parent which is red having a child who is also red. So there shouldn't be any red combination. Now every path starting from the root node till the null node. Okay, I'll explain you what is null node, but just understand that every single branch that forms from the root node till the null node has to have equal number of black nodes. This is also very important constraint. Now, also the last point, that every null leaf node is black in color by default. So this is a property. So now let's understand this with the help of few examples. So you can see in this particular case, I have three examples of red black tree, and every single tree is satisfying all the properties and constraints of red black tree. So you can see the first property, that every single node has to either be of red color or black color. So you can see that is satisfied. Similarly, the root node has to be black in color. So you can see that is as well satisfied. Then there shouldn't be any parent-child red conflict. So you can see there is no parent and child, okay, that is having both red colors, right? So there's no combination like that. Then the last point and most important constraint. Okay, so the second most important constraint was that from the root node, if you come till the leaf node, so you can see phi is the leaf node, but obviously you have one more leaf node, that is null leaf node. So in this case, every single tree is going to have this null leaf node, right? It is called null leaf because it is not having any value, and every single null leaf node is going to be black in color. You can see that. So every single path from the root node till the null leaf node has to have equal number of black colors. So you can check that out from here. If I start, it's 1, 2, 3, 1, 2, and then 3. It's again 1, 2, 3, 1, 2, 3. Then you can see 1, 2, and 3. Just follow my pointer. 1, 2, and then 3. 1, 2, and then 3. And again here 1, 2, and 3. Similarly here 1, 2, and 3. 1, 2, and 3. 1, 2, and 3. If you go for the next example, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, and 3. Similarly, if you check out for the left subtree, it will be left tree, red black tree, it's going to be the same. So that's for you to check it out. You can pause the video and you can check them out. Now proceeding ahead, so we are going to understand the rules of insertion in red black tree. Now, so the first and the most important rule, that if the tree is empty, then you have to insert a new node inside the tree, and it has to have a black color because that node becomes the root node. So root node obviously has to be black in color. That is the property as well as the constraint of red black tree. Now, if the tree is not empty, then the real work starts. That means you have to create a new leaf node following the rules of insertions of binary search tree. So what is binary search tree insertion? That if the node comes, if it is less than the parent, it has to go to the left, and if it is greater than the parent, then it has to go to the right of the parent, right? But now in this case, we have to see to it that is this marked with red color. So every node, new node, which gets added as the leaf node has to be red in color. Now, the next point is checking the parent of the new node. So we know that there shouldn't be any red parent-child relationship. So when we insert the new node and we check the parent, if the parent is the black color, then we have to do nothing because it is not violating the property of red black tree that no like there shouldn't be any parent child red relationship. So if it is black, the parent is black, it is not violating. But if the parent is red, then we have certain rules to follow to ensure that you make it a proper red black tree. That means we have to follow certain process to make it a proper red black tree, right? So let's get started. So what do we check? We check the parent sibling. Okay, that means when we are working with the parent and the parent is red, then we have to check the sibling of the parent. Now, the sibling of the parent could have a black color or there could be no sibling at all. So, if this is the case, that the parent is having either a black child or a null child, so in that case, we are going to perform rotations. So, there are four types of rotations as we know in avial trees. So, the same rotations we are going to adapt over here, and the same rules like the grandparent, the parent, and then the child. And accordingly, you have to figure out which kind of rotations you got to do, and you have to perform the rotations. But in this case, we are also going to perform some recolorings. So if it is LL or an RR rotation, then you have to first, before performing the rotation, you have to change the color of the grandparent and the parent, and then you have to proceed for the rotation. If it is a LR rotation, then you have to first perform the left rotation from below, then you have to recolor the grandparent and the parent, and then you have to perform the right rotation. If it is a RL rotation, then you have to perform the right rotation from below, then you have to recolor the grandparent and the parent, and then you have to perform the left rotation. What if the parent and its sibling, right? If the sibling of the parent is having a red color, if the sibling is having a red color, then you have to recolor both parent and its sibling, right? That means the sibling of the parent, you can call him uncle. So you have to color both the parent and the uncle, right, with black color. And then you have to again check for your grandparent. If the grandparent is not the root node, then you have to recolor that as well. And then again you have to check whether you are violating any property of red black tree. So this is how you proceed. So in this case, uncle is the most important. Every single time you'll be going to your parent and you'll be checking from your parent's sibling, who is your uncle, which color he has. If he has a black color, then there is no uncle, then you have to perform these particular steps. If he is red in color, then you have to perform the next set of process. So I hope you have understood that if the uncle is actually red in color, then you can recolor both the parent and its sibling, right? So uncle and your parent, and then you can recolor the grandparent also if he is not the root node. If he is the root node, then obviously the property that the root node should be black has to be applied. So you can't recolor it. You can do nothing. So let's get started now. In this case, we are going to form a tree with these particular elements. We'll start from 8 and then we'll go till 55. So let's understand how the insertion is going to happen. So now the first step, now I'm going to insert 8. So you can see as I insert 8 and 8 is a root node. So it has to be black. So the first property is satisfied over here, that the root node has to be black. And obviously the null leaf node, they are black in color by default. This was the fifth point in the properties. Now let's start with inserting 15. So where would 15 go? You know that 15 is greater than 8, so satisfying the properties of the binary tree, it has to go to the right of 8, right? So let's insert it, and you know that when we insert a new node, it has to be in red in color. As this particular new node is red in color, let's check whether it is violating any properties of red black tree. So you can see that the number of blacks from the root node, they are same, that is 2. So this is first, this is second, this is first, this is second, this is 1, this is 2. So it is satisfying the property of number of blacks in each branch. Do we have any parent-child red-red conflict? So no, 15 is red, but obviously the parent is black. So there is no red-red conflict. So let's understand by insertion of the next element. So we are going to insert 5 in this particular tree now. Okay, so let's insert 5 and we'll see that 5 comes to the left because it is satisfying the insertion property of binary tree. So you can see 5 comes to the left of 8 as it is less than 8. And again, nowhere it is violating any rules of red-black tree. So now in this particular tree, we are going to insert the next element, that is 11. So let's check how we insert 11. Now, when we insert 11, as 11 is greater than 8, it goes to the right. As it is less than 15, it comes to the left. But now, here we see that we have a red-red conflict. So how should we proceed? By understanding the rules. So obviously in the rules it says that check the uncle of the parent. So 11 is the new node. Who's the parent? The parent is 15. Who's the uncle for 11? So it is the parent's sibling. So 15 sibling is 5. Who is the uncle of 11? Now, so as the uncle and the parent both have the same color, that is red, we can recolor them. True? Yes, it is. So let's check out the rules one. So if the uncle is red, then what do? We recolor both parent and its sibling, right? That means the parent and the uncle to black color. Then we go towards the grandparent, and that is the parent's parent. And if it is not the root node, then we recolor it too. And then we again recheck whether it is violating any rules of red black tree. And accordingly, we can process with the help of the rules. But the thing is, if the grandparent is the root node, then we can't do anything. Okay, we need not change anything. So you can see the last point, it is saying the same thing. So let's understand. So here, how are we going to proceed? We are going to recolor both my parent and the sibling. That means parent and my uncle, right? Now, so I recolor them, they both go black. And then I try recoloring the grandparent also. But do you think this is right? Do you think we should be recoloring the grandparent? The thing, it will violate the property of red black tree. So obviously it should obviously be black, and so we again recolor it to black. So now you can see it is a balanced red black tree. In every single branch we have equal number of blacks, and we don't have any red black parent child relationship. Sorry, red parent child relationship. So now, which is the next element that we got to insert? So we had inserted 11. Now we'll try inserting 13. So you can see this is the tree that is there from the last slide. And now we are going to insert 13. So where would 13 go? As 13 is greater than 8, it will go to the right. As it is less than 15, it will come to the left. As it is greater than 11, it will go towards the right of 11. So you can see that it is going to the right of 11. Now, again you can see it is violating the property of red-black tree because you have red-red parent-child relationship. Now, so who will 13 look for? He will look for his uncle, right? That is the sibling of the parent. Who is the parent? 11. But do you have an uncle in this case? The thing is, you don't have an uncle in this case. So what you should do? Now you should follow the rules of the rotation of aviary tree. So now in this case, if this is the child, this is the parent, and this is the grandparent. So what kind of rotation you got to follow? So this is the LR rotation. So you can see from the parent till the grandparent, it is left, and from the parent to the child, it is right. So it is LR rotation. So how should you perform this rotation? I had explained you that we perform the left rotation from below, then we recolor the grandparent and the parent, and then we perform the right rotation. So let's see how it works. So you can clearly see it is written over here. In LR rotation, we perform the left rotation from below, then we recolor the grandparent and parent, and then we perform the right rotation. So how it is going to happen? So that means first I have to perform the left rotation. As we perform the left rotation, the 13 will go up and 11 will come to the left of it. So let's see how will it look like. So this is how 13 comes up. Okay, so it's a rotation which is happening towards the left side. So it is starting from below. Okay, so obviously it will be 13 and 11 to the left of it. Now you got to recolor what? The grandparent and the parent. So the grandparent is 15, which is black. I'll make it red. The parent, which is 13, is red in color. It will go to black. So you'll see 13 going black. Okay, so now you can see that 13 is going black and a right rotation took place, right? So it is LR rotation. So we performed we can say we performed the left rotation here, then we recolored, and then we are performing the right rotation. So this is how the tree would look like, right? Now, so now this is a balanced red-black tree. We have number of blacks which is same in every branch, and we don't have any red-red parent-child relationship. So now let's start inserting the next element. So after 13, we are going to insert 37. So let's see how we'll insert 37 in this particular tree. So here we have the tree. We are inserting 37. Where will 37 go? It will go to the extreme right because it is even greater than 15. So you can see it will look like this. Now again, it is a red-red parent-child conflict. Now in this case, who will 37 look for? He'll look for his uncle. Yes, he has an uncle. And the uncle has the same color as that of the parent. That is, both are red. In this case, what do? We recolor them both. And we also recolor the grandparent if he's not a root node. So now in this case, I'll have to make both the parent and the uncle as black and node 13, who is the grandparent, as red. So let's check out. Does it say the same thing? Yes, it does. If it is the red color, then you have to change both parent and sibling to black color, and the grandparent, okay, he has to be recolored, and then we have to recheck. So let's check. So here you can see I have converted them both to black and have converted this particular node grandparent to red. And now I recheck. What do I recheck for? I recheck that is it now violating any rules of red-black tree. So you'll see it is not. Okay, every single branch is having number of blacks as 3. Okay, and there is no red-red parent-child conflict, and my root node is also black. So yes, I can proceed now. So which next element I'll try to insert? 37 is inserted. So next 28. So you can see when I insert 28, where will 28 go? It will go to the left of 37, right? So you can see it is inserted here. Now, again, we have a red-red parent-child conflict. Now, in this case, what should I do? You can see 28 will look for the sibling of the parent. So the parent is 37. Who is the sibling of the parent? It is a null leaf. That means 28 doesn't have any uncle. As 28 doesn't have any uncle, what do we got to do? We got to perform some rotation. So what is that rotation? This is the child, this is the parent, this is the grandparent. So what kind of angle it is making? It is making a right rotation, right direction first, then the left direction. So it is RL rotation. RL rotation. And how do we perform an RL rotation? We start with the right rotation from below and then the left rotation at the top. Okay, so let's see the rules. So if it is an RL rotation, we have to perform right rotation from below. Then we have to recolor the grandparent and the parent. And then we perform the left rotation. So let's get started. Now, we have to perform a right rotation from below first. So 28 will come here. 37 will go to the right of 28. So let's see how this works. So this will look something like this. 28 goes up, 37 comes to the right of it. Now, After this, we recolor. Who do we recolor? We recolor the grandparent and the parent. So 28 will turn black, 15 will turn red. Please remember this. 28 will turn black, 15 will turn red. So you'll see that happening over here, right? And we'll be performing the left rotation as well. So when we perform the left rotation, 15 comes down, 28 goes up, 37 as well goes up. So you can see 28 goes up, 15 comes down, right? And you can see the color has been changed, right? So now 15 is having red and 28 is having the black color. Let's proceed by inserting the next element. Now what is the next element? That is 43. So where will 43 go? 43 is the heaviest element, I guess. So it'll go to the right of 37. So you can see it has gone to the right of 37. Do we have a red-red parent-child conflict? Yes, we do. In this case, I'll look for the uncle of 43. Who is the uncle of 43? 15. Yes, and uncle is having the same color as the parent, right? So what is the rule? If it is same, then we have to recolor them both as well as the grandparent, if the grandparent is not the rule. So let's check out how do we work it out. So you can see here we have colored both of them and we have changed the grandparent. So 28 was black first, now it is red. And then we recheck. Do you remember? So rechecking means, is it creating any issue? Yes, it is. You can clearly see it is again creating a red-red parent-child conflict. So how will we ensure that this goes away? So again for 28, we have to check for his uncle. Now the uncle of 28 is what? 5. So the sibling of the parent is 5. Now this is black in color. So obviously I have to perform some rotation. So let's check which rotation. So this is the grandparent in this case. Okay, this is the parent that is 13 and this is the child who's 28. Right? So in the red-red relationship, if this is the child, this is the parent, this is the grandparent. So it is right rotation. In this case, we'll move left. We'll rotate left. But before rotating left, we have to recolor what? The parent and the grandparent. So let's look at the rule. If it is LL or RR rotation, then recolor grandparent and parent and then rotate. So you can see I'll be recoloring 8 and 13 first. So 13 will go black and 8 will go red. And then I rotate. So it is rotating left and you can see, and the left child of 13, okay, where it will go? It will become an orphan. So obviously following the rules of Avian tree, left child of 13 has to become right child of 8. So you can see 11 has got attached to 8 to the right of 8, right? Now let's insert the next element, that is 47. So where will 47 go? It is the heaviest element now, and it will again go towards the right of 43, right? So it's a red-red parent-child conflict. Now 47 look for his uncle. Who's the uncle? There is no uncle. It is a null leaf node. So now in this case, obviously I have to perform some rotation. Which rotation I need to perform? So you can see if this is the child and this is the parent in the red-red parent-child conflict, then 37 is the grandfather. If 37 is the grandfather and it is a RR rotation, then first we have to recolor the grandparent and the parent, and then we rotate. So obviously, in this case, we have to recolor 37 and 43 first, and then we rotate which? Left side, right? So you can see that 37 will become red, 43 will become black, and then we'll rotate left. So this is how it will look like. 37 coming down, 37 becoming red, 43 becoming black. Okay, so now let's proceed by inserting the next element, that is 4. So you can see where will 4 go? It is less than 5. So it will surely go to the left of 5. Now, when we insert 4, is it any way violating the rules of red-black tree? It isn't. So obviously there's no rotation, no recoloring that we need to do. You can see the number of blacks is also maintained and there is no red-red parent-child relationship. So the next will insert 2. So you can see 2 will go to the left of 4 as well because it is lesser. As 2 goes to the left, and now again see it's a parent-child relationship which is violating red-red. Okay, so 5 becomes the grandfather. Now what kind of rotation are you going to perform? It is LL rotation. So LL rotation, that means you have to move towards the right hand side. But before that, we recolor the grandfather and the father, right? Grandfather and the parent. Now, so grandparent is black, you'll make it red. The parent is red, you'll make it black, and then you rotate towards the right hand side, right? So this is it. This point we are going to execute, and you can see it will be a right rotation now, and this is how it will look like, right? So I have performed inserted 2 as well. The last remains, that is 55. Where will 55 go? 55 is the heaviest, so it will go towards the right, right? So you can see 55 is inserted here. Now when 55 is inserted here, it's again violating the red-black parent-child relationship. It's red-red parent-child. So it's violating. Now, what do I need to do when I see red-red parent-child? I need to see the uncle. So what is the uncle? Uncle is 37 and red in color. So now with the rules, I got to recolor them both, the parent and the uncle and the grandparent as well. As grandparent 43 is not the root node. So let's start. So you can see I've recolored them both and I've recolored the grandfather as well, the grandparent. When I recolor the grandparent, I have to recheck whether I'm violating any rules of red black tree. Am I? Yes, because again you can see a red-red parent-child relationship. So now 43 has to check for his uncle, that is the sibling of the parent. And yes, that is also having a red color. So if the parent and the uncle both are red, what do? We recolor them both. So obviously I'll recolor them both and I'll recolor the grandfather as well. But can we recolor the grandparent in this case? We can't, because the grandparent that you can see is a root node. Okay, so let's see what would the output would be. And you can see I have recolored them, but I can't recolor the grandparent as it is the root node. So yes, this is how we reach the final stage. Now we can revise the entire working. Okay, so let's get started once again. We inserted 8, then we insert 15, which goes to the right, and it's not violating. Then we insert 5, which comes to the left. Still, it is not violating. Then you can see that we insert 11 and it is violating. In this case, I look at the uncle, uncle of the new node. Uncle of the new node is the same color as that of the parent, which is red. As we see this, what do? We recolor them both and we recolor the grandparent as well. But grandparent is what? The root node, so we can't recolor it. So how will it look like? I'll try to recolor it, but it shouldn't be, so it will again become black, right? Now after this I'll insert the new node. After 11 I'm going to insert 13. So where will 13 go? To the right of 11. Now as it goes to the right of 11, you can see it is again violating the property of red-red parent-child relationship. There shouldn't be any red-red parent-child. So now who will 13 look for? 13 will look for his uncle. Is there any uncle in this case? No, there is no uncle for 13. So in this case, what do we need to do? We need to find out which kind of rotation will perform. So the rotations are same as in Avian. So you can see it is this is the parent and this is the child. So this becomes the grandparent. So it is left-right rotation. In left-right rotation, I perform the left rotation from below, then I recolor the grandparent and the parent, and then I move for the right rotation. So you can see that happening. Okay, so this is what it is. Then you can see that I first perform the left rotation, then I recolor the parent and the grandparent. So 13 becomes black, 15 becomes red. And then I rotate right. So you can see 13 is black, 15 is red, and the right rotation has been performed. Now, after this case, I'll insert the next element, which is 37. So where will 37 go? It will go to the right of 15. As it goes to the right of 15, it is violating the red-red parent-child relationship. And the uncle in this case is also red, so I can recolor them both. And even the grandparent, as the grandparent is not the root node. Now, after doing the entire thing, are we violating anything? No, we are not. So it is a perfect red black tree. Now let's insert the next element, that is 28. When we insert 28, it goes to the left of 37 and it is violating the parent-child relationship as they were both red in color. In this case, 28 will look for his uncle. There is no uncle. So I have to perform certain rotation. That is right-left rotation in this case, because this is the grandparent and we come to the right and then we come to the left. How do we perform right-left rotation? We perform the right rotation from below, then we recolor and then we perform the left rotation. So you can see that I'll perform the right rotation first. So right rotation means 28 will go up, 37 will come down. So this will look something like this. Then I recolor the grandparent and the parent. So 28 is going to be black, 15 is going to be red, and then I'll rotate left. So this is how it will look like after the rotation. Now, insertion of 28, I'm going to insert the next element, that is 43. So when I insert 43, where will it go? It will go to the right of 37. Again, it is violating the rules of red black tree. So now, how will I proceed? So you can clearly see that I'll first recolor both the parent and the uncle, and then I recolor the grandparent as well. So this is how it will look like. But again, it is violating the rules of red black tree as I recolor the grandparent. So now in this case, what do I need to check? 28 will look for his uncle. Uncle is black. As uncle is black, I need to perform the rotations. Which rotation? So you can see this is the grandparent, this is the parent, and this is the child. So this is RR rotation. That means you have to move towards the left. But before doing RR rotation, you need to what? Recolor the parent and the grandparent. So 8 will become red, 13 will become black, and then the rotation would be performed. Right? So this is how it will look like. It is a left rotation after recoloring. Right? Now, after we insert 43, we need to insert what? 47. So again, 47 goes towards the right, and again you can see it is a conflict. When it is a conflict, 47 will look for his uncle. There is no uncle, so I have to perform the left rotation. As you can see, this is right rotation, RR. So when I'm moving towards the left, first I have to recolor. So 37 will become red, 43 will become black, and you can again see this is how it will look like. Okay, so after I've inserted 47, I'll insert 4. So you can see when I insert 4, it comes to the left. And when it comes over here to the left of 5, it is not violating any rules of red black tree. Now I'll insert 2. After inserting 2, 2 will come to the left of 4. So then it will surely be violating the rules of red black tree. And in this case, this is the child, this is the parent, so 5 is the grandparent. So it is left rotation. That means you have to move towards the right. When you're moving towards the right, before moving, first you have to recolor the grandparent and the parent. So that means 4 will become black and 5 will become red. So you can see 4 becoming black, 5 becoming red, and then the right rotation took place. Right? Now, let's insert the last element, that is 55. So you can see that I will insert 55 towards the right of 47. So this is how it will look like. It is violating the rule, and the uncle of 55 is also red, so I have to recolor them both, and I have to recolor the uh, grandparent as well. So you can see after recoloring, grandparent is becoming red, the parent and the uncle are both black. Now in this case, 43 is the child, 28 is the parent, and there's a parent-child red conflict. So now let's check out the uncle of 43, who is 8. He's again red in color. So it means I can recolor both parent and the uncle. And I have to recolor the grandparent, but in this case we can't, as it is the root node. So you can see finally this is how the insertion will look like. So I hope you have understood the insertion of red black tree. This is it. I hope you have understood the entire rotations and the recoloring. So if you have understood the concept of insertion in red black trees and how red black trees is having fewer rotations than AVL tree, so I'll be covering this part of complexity difference between red black tree and AVL trees in the further videos. So kindly like, share, and subscribe this video if you have liked it. Happy learning, enjoy advanced algorithm. Thank you.